The purpose of this video is to introduce what are known as harmonic functions, which have applications in physics. So a harmonic function is a function that maps from R2 to R. It's a multivariable function. That means it's the type of function we study in Calculus 2. It has nothing to do with complex functions, at least for the time being. The Laplace operator on a function is defined by adding together the two non-mixed partial second derivatives. So in particular, we use this notation, this fancy upside down triangle. The Laplacian is defined by taking the second partial of phi with respect to x, the second partial of phi with respect to y, and adding the two quantities together. So let's take a look at an example. If phi of x is x to the third plus xy plus y to the third, the first partial with respect to x would be 3x squared plus y. The first partial with respect to y would be x plus 3y squared. So if we took the partials again, the second partial of phi would be 6x, and the second partial of phi with respect to y would be 6y. So that means the Laplace operator of phi of xy equals this function is equal to 6x plus 6y. So the Laplace operator is a fancy second derivative of sorts for a multivariable function. Now here's the new definition. Suppose we have a set D in the R2. Now of course we can view R2, sort of identify it with a complex plane, but we're thinking of a function defined in R2. And suppose that phi is a function defined on R. So again, it's a multivariable calculus function. We say that phi is harmonic on D, provided its Laplace operator is equal to 0 in D. So for example, let u of xy equal x squared minus y squared. This is defined in all of R2. The second partial of u with respect to x is 2. The second partial of u with respect to y is negative 2. And so if we add those two together, we get 0. So that means that the function x squared minus y squared is harmonic in all of R2. Now the function u of xy equals x to the third plus xy plus y to the third is not harmonic in R2, and that is because we calculated its Laplacian above, and the Laplacian was 6x plus 6y, which is not equal to 0 on all of R2. Now let's suppose that D is a region in the complex plane, and f maps from D into the complex plane, and it's a function. We can always write f in terms of its real and imaginary parts, where z is equal to x plus iy. This is something we've done several times. Then, under the assumption above, if f is analytic in D, then both u and v are harmonic in D when viewed as a subset of R2. We say that u and v, they're related to one another. They are harmonic conjugates of one another. So one thing to keep in mind is that this D here is a subset of the complex plane, and we're viewing f as a function that's analytic in D. But of course, we can view D as also a subset of R2. Thinking about this another way, when we view D as being in the complex plane, we label its axes as the real and imaginary axes. If we view this as a subset of R2, we would label its axes the x and y axes. So here's an example. Suppose that f of z equals z squared. This is an entire function. It's analytic everywhere. Let's take a look at f of z. Let's break this down into its real and imaginary parts. The real part works out to be x squared minus y squared, and the imaginary part is 2xy times I. By the theorem, both x squared minus y squared and 2xy, the real and imaginary parts, they are harmonic in all of R2. And actually on the previous page, we actually verified this was harmonic by showing its Laplace operator is 0. So these two functions, they are harmonic, and because they form the real and imaginary parts of f, we say they are harmonic conjugates. Now we're going to prove this because it's a simple proof that uses the Cauchy-Riemann equations. So we know that u the partial of u with respect to x is equal to the partial of v with respect to y, and the partial of u with respect to y is minus the partial of v with respect to x. And that's true in all of D. That's because f is analytic in D, and because when a function is analytic, the Cauchy-Riemann equations have to hold. So let's focus on u just for a moment. And we'll assume its mixed partials are derivative. All mixed partials, second mixed order partials are derivative. So the Laplace operator of u is defined to be the sum of the two unmixed second partial derivatives. Now when we take the second partial of u with respect to x, that's the same as taking the first partial with respect to x of the first partial with respect to x. And when we take the second partial with respect to y, that's the same as taking the first partial with respect to y and then taking the partial of that with respect to y again. But the Cauchy-Riemann equations say that the first partial with respect to x is the first partial of v with respect to y, and the first partial of u with respect to y is minus the partial of v with respect to x. Now notice what happens here. We're taking the partial of v with respect to y and then x. We're taking the partial of v with respect to x and then with respect to y, and we are subtracting, the two. Now, for most cases, the two mixed partials will be equal, in which case we get 0. So that tells us that if f is analytic, then its real part, u, has to be harmonic. And the same proof actually works for the imaginary part of f. Now, a common problem that we'll be discussing soon in the context of applications is the following. Given a harmonic function on some set of R2, we frequently want to find a function v, also defined in the set, so that v is defined, so that the function f defined by f of z equals f of xy equals u of xy plus iv of xy is analytic in D, when we view D as a subset of the complex plane. So again, we're starting with the function u that's defined in R2. But of course we can view R2 as being the complex plane as well. What we're trying to do is we're trying to find a function v so that the sum of u plus iv is analytic in D. Remember that v and u are called complex conjugates. They're kind of like cousins of one another. So it's sort of like we're starting with u and we're trying to find its cousin v. Let's take a look at an example which kind of illustrates the general principle. Let's suppose that u is x to the third minus 3xy squared plus y. And this is defined in all of R2. Okay, it's easy to check using the definition, taking the second order partials, that this is harmonic there. So now, by the Cauchy-Riemann equations, we know that whatever v is, it's going to have to satisfy the partial of u with respect to x is the partial of v with respect to y. That's because we want this expression, this function, to be f, which is analytic. So that equation is the first Cauchy-Riemann equation, which has to hold. So the partial of v with respect to y has to equal, or we want it to equal, the partial of u with respect to x. And the partial of u with respect to x we can calculate easily. It's 3x squared minus 3y squared. And the derivative of y with respect to x, of course, is 0. So that's the partial of v with respect to y. Now again, we're trying to figure out what v is. So the natural thing is to anti-differentiate this with respect to y. Now, if we anti-differentiate with respect to y, the antiderivative of 3x squared with respect to y would be 3x squared y. The antiderivative of 3y squared would be y to the third. But then we have to add a constant. And we need to be careful here because this constant could depend upon x. For example, if I have an x here, if we had 3x squared y minus y to the third plus x, or sine of x, or e to the x, and we took the partial with respect to y, the derivative of this with respect to y would go away. So we have to keep in mind that there's a term here that depends solely upon x. So that's what v has to be. Now on the other hand, the second Cauchy-Riemann equation says that the partial of u with respect to y has to equal minus the partial of v with respect to x. Now the partial of u with respect to y, we can see from up here, is minus 6xy plus 1. So we want to set that equal to the partial of v with respect to x. And if we do that, if we set the two equal to each other, the partial of u with respect to y is minus 6xy plus 1. If we take minus the partial of v with respect to x, we would get 6xy here. We would get a 0 here when we take the derivative with respect to x, and we would get c prime of x when we take the derivative of this with respect to x. Now notice how the two sides match, and that will be the case if you've done your work correctly. And so this tells us that c prime of x has to equal negative 1. So in other words, c of x is minus x. Now we could add a constant like 5 or 4 to c of x, but we really don't need to because we simply need one function v. So therefore, v of xy is 3x squared y minus y to the third minus x. That's our desired complex conjugate. So again, we took our v up here, and once we figured that c of x was negative x, we just replace that here. So that's our complex conjugate. And we can always check that this is true by actually computing the Laplacian of our result. And our Laplacian operator had better be 0 in order for our answer to be correct. Here are two problems I'd like for you to work on in preparation for class. First, show that the function u of x, which is e to the x times cosine of y, is harmonic in all of R2. You want to do that by showing its Laplacian is equal to 0, and that's going to involve some second-order partial derivatives. And then use the method that I discussed on the previous page to start with the function u of xy minus x plus y, it's harmonic in all of R2, and find a formula for its conjugate v, showing all of your work, of course. So please do these in preparation for class.